I found out that my discomfort is eased if I wear this support, my girdle. Hope I don't have turtles in my girdles or something like that. You know about this. I told you about the extended time which we will provide. And some of you may have a legitimate conflict with the time for exam 1 because, for example, you might, well, wait, you can't have 46 laboratory because we don't have 46 laboratory in spring on Thursday nights. But you might have a laboratory class in a different course. So if you have a legitimate conflict, I will ask that you present me a note which contains your name, your email address, a brief indication of the nature of the conflict, and a statement indicating if you are able to take exam 1 earlier Thursday, starting at noon or 2 p.m. or 3 p.m. in Lee 309, our conference room. Very nice place. With such accommodations, you will be provided the same amount of time to deal with the exam as the evening folks. So if you are in this conflict situation, present the note in writing. Now, on with buffer arithmetic. Reminder, you'll do additional examples of buffer arithmetic tomorrow in discussion class. Be there. Ever so obviously quite germane to the nature and content of exam number 1. 1838. We considered taking an ammonium ion ammonia buffer, which if you recall from the original QPSI contained 0.10 moles of ammonium ion and 0.08 moles of ammonia. We treated that with a 0.020 mole quantity of HCl gas and posed the question after this treatment, what was the pH? pH was 8.95. At this point, since we added 0.020 moles of HCl gas, we converted the amount of ammonium ion in the system to 0.12 moles and the amount of ammonia in the system to 0.060 moles. Now we go to question 39 and say, let's add some more HCl to this ammonium ion ammonia buffer in order to quadruple the hydronium ion concentration. Quadruple it from the value which it has at pH of 8.95, for which the hydronium ion molarity is 4.48 times 10 to the minus 9. Now, with that, we remember or recognize that once again, the reaction that occurs in the system when the HCl gas is added is to consume additional ammonia, turn it into ammonium ion and chloride ion, a reaction for which the extent is clearly 100%. Since ammonia is a stronger base than water and HCl reacts with water 100%. So it surely reacts with a stronger base 100%. This is Ka for ammonium ion. There's the Ka value. This is the quadrupled hydronium ion molarity. I think I said this is the hydronium ion molarity at pH 8.95. That's not true. What we do is to take the hydronium ion molarity at pH 8.95 and multiply it by 4 to get this. This is the hydronium ion molarity we are wishing to produce. Question 1839. Again, the intention is to add HCl gas to the buffer created in 1838 to quadruple the hydronium ion molarity. That gives us this hydronium ion molarity after the hydronium ion molarity for that is quadrupled. Here it is. So, the reaction in question again consumes ammonia, and for each mole of ammonia consumed, we make a mole of ammonium ion. So, this is moles of ammonia, this is moles of ammonium ion. We don't have to change these to concentrations because that would involve dividing the numerator and the denominator by the same value. Waste of time. Simplify the arithmetic, because this Ka for ammonium ion divided by this, the quadruple hydronium ion molarity is 0.125, or 1.25 times 10 to the minus 1. One unknown, solve it for x, that's the amount of HCl gas to be added. Nothing fancy. Just pay attention to the information given in the statement of the problem. Tell me. At this point, how many moles of ammonia remain in the system? And at this point, how many moles of ammonium ion are in the system? Surely you can add 0.04 to this. The point being, at this stage of the game, no buffer has infinite capacity. What do I do to the buffering effect of this system if I add another 0.020 moles of HCl? If to this system at this point I add another 0.020 moles of HCl, what happens? Practically speaking, all the ammonia is now murdered. And now the pH is going to decrease dramatically. If at this point I said, let's add another 0.020 moles of HCl. Now what would you do to calculate pH? Or what would you do to calculate hydronium ion molarity? What would the Ka relationship for ammonium ion look like? What would it look like?
Would it be the same as the hydrogen produced by 0.060 moles of ammonia?
By how many moles of ammonium ion?
0.060.
Where'd you get that? If I add to this system another 0.020 moles of HCl, that will kill the remaining ammonia and turn it into this. So how many moles of ammonium ion will it now have? 0.18 moles of ammonium ion. What general relationship will now apply to this solution? Will x squared over m sub I minus x now apply? You betcha. Because now I have a solution in which the only solute species of consequence is, guess what? What is it? Ammonium ion, that's right. I now have an ammonium ion solution. 0.18 moles of ammonium ion swimming around in what volume? We'll go back to the volumes of the ammonia and ammonium ion with which we began back in question 1838. I think it was 100 mils of each. So I'd have 0.20 liters, because now I'd have to convert moles of ammonium ion to concentration. Then I could apply x squared over m sub I minus x. Ha ha! But in the laboratory I can do any damn thing I want, provided I have the materials available. What am I going to do to this system if I add 0.030 moles of HCl gas?
You want to have 0.18 moles of ammonium and then you have the remaining 0.010 HCl straight in motion.
So how will the system now inventory? Or, if you wish, let's go straight to the question. How will I now calculate the hydronium ion concentration for this system? I got 0.020 moles of ammonia, 0.16 moles of ammonium ion. I'm going to add 0.030 moles of HCl gas. Will I kill all the ammonia? Yes. Will I turn all the ammonia into ammonium ion? Yes. Will I now have 0.18 moles of ammonium ion? Yes. What will I do to calculate hydronium ion concentration for this system? Will I use Ka ammonium ion? Yes or no? What will I do? How do I get the hydronium ion concentration for this system? Because I will have how much HCl gas not reacted with ammonia? 0.010 moles, right? And that 0.010 moles of HCl, since it's not reacting with ammonia, because all the ammonia got murdered, what's the HCl gas going to react with? Water. And going to make? Hydronium ion. How many moles of hydronium ion will I make? 0.010. And this moles of hydronium ion will be swimming around in what size lake? 0.20 liters, right? Tell me the hydronium ion concentration. Can you divide 0.010 by 0.20? That's all you have to do at this stage of the game. If at this stage of the game you start fooling around with Ka ammonium ion, you are wasting your time. Because once you get an abundance of hydronium ion in there, hydronium ion says to ammonium ion, hey, I'm the boss now. Because now I am a principal species and I'm a hell of a lot stronger ass than you are, ammonium ion. So we won't even remember that you're here when we ask the question, what now is the system pH? How about that? And how do I know all of this stuff? Because as I go through all these treatments, what do I keep in my mind always? QPSI, and that way you win. If you keep a handle on what's in the system, the composition of the system at all times, you win. And if you forget the composition of the system, you are guaranteed to lose. Because you can't do chemistry on the system if you don't know what the hell's in the system. But you know this, don't you? Good. Keep that in mind, because you can rest assured I'll have questions like that for you to entertain you this Thursday. How about that? Now, discussion class. I'm going to jump to question 1843. Since 1843 is a follow-up to 1835. Remember 1835? 1835 was an indicator question. A water solution of methyl acid HQ was treated with mythical indicator HGX. The purpose of which was to determine M sub I for HQ in that solution. And if you recall, we found that to be 0.02. Pardon me, 0.2. Can only get 1 sig fig out of this. Indicator analysis won't let you get better than 1 sig fig. So let's go back to 1835, where we had 0.2 molar HQ solution, and a Ka of HQ of 2 times 10 to minus 2, because in 1835 we said HQ was of the same strength as indicator HGX. And from the color change information for HGX, we found that its Ka was 2 times 10 to minus 2. That's just a restatement of what we've already done. We're going to take this HQ solution, which, if you recall, on treatment with HGX showed us a YG color. Had a pH of 1.3 and a hydronium ion molarity of 5 times 10 to minus 2. That's still question 1835. Question. How much sodium hydroxide do I have to put into this HQ solution in order to develop a distinct green color with indicator HGX? Distinct green with HGX, if you will recall, is pH 1.7, for which the hydronium ion molarity is 2 times 10 to the minus 2. Clearly, if I add sodium hydroxide, the pH is going to go up. Now tell me, what kind of a solution, generally speaking, am I constructing when I add the sodium hydroxide to the HQ solution? Generally speaking, what kind of solution am I making? When I add the sodium hydroxide to the HQ solution. Well, when I add the sodium hydroxide to the HQ solution, what will the hydroxide ion react with? In our HQ solution, would you please tell me what the principal acid is in that system? HQ. Thank you. If you forget QPSI, you lose. So when I put the sodium hydroxide in that system, what's the sodium hydroxide going to react with? HQ. And what will hydroxide ion do to HQ? Turn it into what? Q minus, right? Hydroxide ion looks over at HQ and says, give me one of your H pluses, thank you. Per HQ molecule, hydroxide ion extracts H plus. Will hydroxide ion react effectively with HQ? Yes. Is that a large extent reaction of hydroxide ion with HQ? Yes. You see that Ka value, 2 times 10 to the minus 2? That's a pretty damn big Ka value, isn't it? Even though that's a weak acid. Hey. So treatment with hydroxide ion effectively converts HQ to Q minus. So what kind of solution am I making if I don't chew up all the HQ? HQ, Q minus, buffer. Buffer! Keep mind on QPSI. I'm killing some but not all of the HQ and converting it to Q minus. So here I am now with a solution which has got a fairly high molarity of the acid HQ and its conjugate base Q minus.
Those were weak acids, weak base.
That's a weak acid. Look at a Ka value.
That's a really strong base.
So what? Q minus is not a strong base. I put hydroxide ion in there, it reacted with HQ and turned it into Q minus. Right? See? Now I got a solution, HQ and Q minus. I got a buffer. How about that? Well, back to figuring out how much hydroxide ion I have to add to achieve this. Here's KHQ. Initial molarity of HQ, going back to 1835, which we answered last time, was 0.2. Hydronium ion that I'm trying to achieve is that which corresponds to pH 1.7, 2 times 10 to the minus 2. So, here's the expression. Can you call this x squared over m sub I minus x? In this case? Does this correspond to x squared over m sub I minus x? No. Hell no! Hydronium ion molarity and the Q minus molarity are not equal in this system. Remember? In essence, I made a buffer. Well, the arithmetic is simple. The Q minus molarity at a pH of 1.7, the hydronium ion molarity of 2 times 10 to the minus 2 is 0.1. Now then, if you go back to 1835, for the 0.2 molar HQ solution, remember that was m sub I? What was the actual molarity of HQ in that solution? Was it 0.2? From 1835, or with 1835, x squared over m sub I minus x applied, didn't it? Because 1835, all we had was HQ as the solute. And we found that YG color on treatment with HGX, hydronium ion molarity of 5 times 10 to minus 2. That's going back to 1835. So what was the Q minus molarity? 1835. 5 times 10 to minus 2, isn't it? X squared over m sub I minus x. How about that? So what was the actual molarity of HQ? The solution molarity of HQ in 1835. It wasn't m sub I. That's the label on the bottle. It was 0.15. Right? It was 0.2 molar, the label on the bottle, less the amount you converted to Q minus. And you converted, you made how much Q minus? How much Q minus we have in 1835? 0.05. 0.2 less 0.05. 0.2 less 0.05. Let me get out my abacus, my IBM mainframe, and all this. Fuses exploding and power lines bursting and all that stuff. To come up with a value of 0.15. And now, I wish to have a Q minus molarity of 0.1. This is 1843. How much Q minus did I have in 1835? 0.05. And when I put the hydroxide ion in there, from the addition of sodium hydroxide, this is the chemistry which occurs. What's the extent of that reaction? 100%, practically speaking. Here's how much Q minus I had in the pot, moles thereof, before I put in the hydroxide ion. Here's how much Q minus I want to have, because we made the arithmetic simple by focusing on a 1 liter solution. So moles and molar concentrations were the same. This is how much I want to have. 0.1 moles of Q minus. I had 0.05 moles of Q minus. So how much hydroxide ion did I have to add? Add 0.05, right? I had to make another 0.05 moles of Q minus. Right? 0.05 plus 0.05. Calculate, scratch paper, erase, figure. Ha! That's what we get. Right? 0.05 plus 0.05 is this. Done. It all comes from QPSI and no place else. Now we jump to the next special topics. Because when we started buffers, we started to talk about special topics involving Bronsted-Lowry acid-base systems, or solutions if you prefer. You're in the lab. You see a bottle bearing this label. Then you look about and you see another bottle bearing this label. As a student of chemistry, you're asked the question, what's the pH for these systems? Now I know in this system, I have created 3 times 10 to the minus 8 moles of hydronium ion per liter of solution, because the HCl reacted 100%. And I know in this system, per liter of solution, I have 5 times 10 to the minus 8 moles of hydroxide ion supplied by solute sodium hydroxide. Okay so far? Are you going to tell me that this solution has a hydronium ion concentration of 3 times 10 to the minus 8? Because if you do, you're going to tell me that an acidic solution is basic. And I will say your score for this response is minus 1,000. And if you tell me for that second solution, the hydroxide ion molarity for the solution is 5 times 10 to the minus 8, you will have told me that the basic solution is acidic. Because if the hydroxide ion molarity is 5 times 10 to the minus 8, the hydronium ion molarity is bigger than 5 times 10 to the minus 8. Because of Kw. And now I'll take off 2,000 points. Because I'm a bastard when you do stuff like that. Because what you've done is to reject chemistry. You're looking for some simple way to grind an answer by pushing buttons without thinking. And that doesn't fly. But you know that. You know that now. Ain't none of that 2045 nonsense going on in here. I know what the hell's going on there. I'm going to get it fixed if I can. If I could make the rules, at this here university, every student taking 2045 would have one lecture and one lecture only. Guess who that would be? You're looking at him. That's it. You wouldn't have a choice. You want 2045, you do it with Horvath. Period. And we'll find out in short order fashion if you got what it takes. But you know what? I'll bet you all you got. All of you have what it takes. But if you're not put in a situation where you have to put to use what you got goes to rot. Like this, when you do arithmetic that you should do here with this. Don't do that. You're spoiling yourself. Today's sermon. Now then, what we're looking at are two solutions where to calculate the system pH, or the hydronium ion concentration, what do we have to consider for these solutions? That's right. You got to consider Kw. Must consider Kw to get pH for the dilute solutions. So let's write it. Now, the solution for calculation, correct calculation of pH for the 3 times 10 to the minus 8 molar HCl solution is in the notes. I trust you've looked at it. If you're keeping up, as you are directed to do, you've looked at that in preparing yourself for today's friendly chat. So let's look at the 5 times 10 to the minus 8 molar hydroxide ion system. What do we have to realize? We have to realize in the 5 times 10 to the minus 8 molar sodium hydroxide solution, we have one source of hydronium ion, but two sources of hydroxide ion. Right? The single source of hydronium ion is the autoionization of water. So we'll call it X. And the stoichiometry of this reaction tells you, as this reaction proceeds left to right, if it creates X moles per liter of hydronium ion, it also creates X moles per liter of hydroxide ion. But that ain't the solution hydroxide ion molarity. That's how much this reaction creates. What is the solution hydroxide ion molarity? It's the sum of the two sources, X plus that. So there's what we got to solve. What chemistry should we think about in solving this? Should we not first realize that this solution is very dilute? Given that it's very dilute, we know without doing any arithmetic, because chemistry tells us so, that the value for x is very close, if not equal to, what number? 1 times 10 to the minus 7. Because a very dilute solution is a solution which is very much like pure water, isn't it? How about that? Pure water, 1 sig fig, hydronium ion molarity is 1 times 10 to the minus 7, just like the hydroxide ion molarity. So in solving, we now know immediately how to couch our speculation for x. If it's not 1 times 10 to the minus 7, it's going to be a number which is going to be close to 1 times 10 to the minus 7. Is it going to be a little bit bigger or a little bit smaller than 1 times 10 to the minus 7 for this system? A little bit smaller. The system's basic, right? So the hydronium ion molarity cannot, under any set of circumstances, exceed 1 times 10 to the minus 7. So tell me a value for x that's somewhat smaller than, but close to, 1 times 10 to the minus 7. I'm listening.
8 times 10 to the negative 8.
8 times 10 to the minus 8 is right on the nose. Let's put it in and find out. Try x. Now then, this is 8 times 10 to the minus 8 times 13 times 10 to the minus 8. Watch out. Here comes the hard part. What's 8 times 13?
65.
What's 8 times 13? 104. So I get 1.04 if I stretch the 3 sig figs times 10 to the minus 14. You agree that's pretty close to kW? The 2 sig figs, it is kW. If you try x equals 7 times 10 to the minus 8, you'll get a value that's ever so obviously smaller than kW. And if you try 9 times 10 to the minus 8, you'll get a value that's ever so obviously larger than kW. That's it. That's all there is to this. Nothing difficult if you keep your mind on the chemistry. And so, I ask now that you look at page 1839. Max percent ionization, Ka in dilution. You can also write in Kb. We have recognized as we dilute a water solution of a weak acid or a weak base, what do we do to ionization extent? Increase it. Now, if we dilute to the extent of saying the solution is infinitely dilute, practically speaking, what kind of solution do we have? Water. So at infinite dilution, what is the hydronium ion molarity for a solution of any acid? What is it? 1.0 times 10 to the minus 7 to 2 sig figs. Hydroxide ion molarity, same value. So with that in mind, there's a derivation given to you on this page. You can look through the derivation. I see no point of repeating it because it's on the page. Showing you how we can arrive at an expression which shows us how max percent ionization for a weak acid depends on Ka for the acid. And you can rewrite the expression and just put in KB in place of Ka to find out how dilution operates on ionization extent of a weak base. This expression is on the information sheet. It's an expression which, again, I expect you to be able to use, but you don't have to memorize it. You don't have to memorize its derivation. I see that at this stage of the game to be pointless. You know, when you're up here teaching this stuff, then you need to know that, how to derive it. Don't worry about that yet. Your job now is just to appreciate the meaning of the expression and be able to put it to use. One more statement. As you look through the information on this page, you'll find something that is very significant about a Ka value of 1 times 10 to the minus 7. Has anyone noticed the significance of Ka value 1 times 10 to the minus 7? The significance is, if a weak acid would have the Ka value of 1 times 10 to the minus 7, at infinite dilution, to what extent will this weak acid be ionized? 50%. Now what does that mean? That means if you have a weak acid with a Ka value larger than 1 times 10 to the minus 7, you can get it to go past 50% ionization extent by dilution. But if Ka is smaller than 1 times 10 to the minus 7, I don't give a damn how dilute the system is, you can't get it to 50%. And if Ka is about 10 times or larger than 1 times 10 to the minus 7, under extremely dilute conditions, you can get that stuff to go, practically speaking, 100%, within the range of 1 or 2 significant figures. Like acetic acid. Ka is 1.8 times 10 to the minus 5. That's 180 times bigger than 1 times 10 to the minus 7. If you take 1 times 10 to the minus 7 molar acetic acid solution, it's ionized 100%. Shortly we'll do the arithmetic to demonstrate that. In any case, I've said to you now the statements of consequence regarding this information. There's the expression for max percent ionization at infinite dilution, showing you how it depends on Ka. Take a look at question 1846. 1846 is nothing but a plug and chug exercise. I rarely do these, but here's the case where I just want you to do a little bit with this expression on the previous page about the relationship between max percent ionization and Ka. The values are there. 1846. Now 1847. I have an acid with a Ka value less than 1 times 10 to the minus 7. How about this acid? Can I do something to get this acid to ionize to an extent which exceeds 50%?
No.
Be careful. Yeah. By dilution, no. But can I get this to go to a reaction extent which exceeds 50%? Hell yes. Reacted with a base that's stronger than water. Better watch out for this stuff. If I put this together with hydroxide ion, I'm looking at a reaction which, practically speaking, is 100%. All right? Now then, let us lay a little bit of foundation for the last stuff for which you'll be responsible on exam 1. And that is calculating the hydronium ion concentration for the most common polyprotic Bronsted-Lowry acid, specifically sulfuric acid. This begins on page 1841. What I want to do is to write the relationships right now, which you have to pay attention to wrestle with this system. There they are. These are the reactions of consequence when you make sulfuric acid solution. What's the extent of the first reaction? 100%. That means that the hydronium ion concentration for any sulfuric acid solution is at least the numerical value that you see on the bottle, m sub I. And this one's governed by equilibrium. So if you look at the stoichiometry of this, you'll see that by this reaction, for each mole of hydronium ion produced, you make a mole of sulfate ion. You know what that means? That means in any sulfuric acid solution, this relationship holds. We'll pick it up from this point next time. You'll go forward with